Jai Hind, Vande Mataram, Namaste. This is Kunal Mehta from Make Me Scientific, and in this video we are going to deal with the numericals of refraction of light chapter. So basically students have a confusion related to the numericals wherein the Snell's law is applied, wave equation is applied. So I'm going to try my level best to ease off your problems. So let's start. So let's say this is air, the first medium be air, or you may also call vacuum. For the easiness of solving the numericals, we are going to consider the speed of light in air and vacuum to be the same, that is 3 into 10 raised to 8 meter per second. So here the speed of light is represented by c, that is 3 into 10 raised to 8 meters per second. And then the ray of light falls on the surface, and say for example it goes inside the glass. So it will definitely bend towards the normal. This is glass. Now wherever you have incident ray, that is medium number 1, so medium number 1 is air, and then you have medium number 2 as glass, and the speed of light over here is, let's say, Vg, correct? The angle of incidence is I, the angle of refraction is R. Then refractive index is always calculated for the second medium, that is glass, and that too with respect to the first medium, that is air. That is equal to speed of light in medium 1, that is C divided by Vg. This is the formula. That is also equal to sin I upon sin R. Now I would like to make a point over here that the frequency of this light, because these lights are anyhow the waves, so the frequency is f, and the wavelength in air, that is lambda a. Now when this ray of light goes inside the glass, in the denser medium the speed decreases, the wavelength decreases. So now the new wavelength over here is, say for example, lambda g, correct? And I can use very well the wave equation c is equal to f into lambda a in the first medium, because the wave equation says that speed is equal to frequency times the wavelength. Here also speed, but the speed in the medium, that is v, is equal to f into lambda g. Frequency multiplied by the wavelength is the speed, but whenever you are plugging in the speed as speed in glass, then the wavelength will be also counted for the glass itself. Now the frequency does not depend upon the medium, it's a characteristic of the source. So that means this can be substituted, these two, equation number 1 and 2, can be substituted in place of c and Vg. So this will become f multiplied by lambda a upon f multiplied by lambda g. So you'll also get the ratio of the wavelength. Okay, fine. Now how to generalize these things? Refractive index of medium 2 with respect to 1, that is always equal to sin I upon sin R. That is equal to speed of light in medium 1. Let me call the speed over here as v1, speed over here as v2. Lambda 1 upon lambda 2. But if I multiply up and down this equation, right, say for example v1 upon v2, multiply up and down by cc, rearranging the v1 upon c times c upon v1. This is equal to refractive index of medium 1 with respect to air, and this is 1 upon refractive index of medium, this is 2, so here 2 with respect to air, and here 1 upon refractive index of medium a with respect to air. So this is 1 upon mu1, mu2, both are absolute refractive indexes. So finally mu2 1, v1 upon v2, lambda 1 upon lambda 2, sin I upon sin R, that is equal to mu2 upon mu1 with respect to air. Now this one is relative refractive index. So this is the formula that you need to remember, and everything will be coming out of these. All the numericals can be solved with the help of this. So now the gallium arsenide has refractive index 4. That means the ray of light is coming from air. Nothing is given, consider the first medium to be air. Then it falls on the boundary, then it bends towards the normal, and it goes inside the gallium arsenide. Now this means that the speed of light here in air was c. Now it reduces by a factor of 4. So here it becomes c divided by the refractive index, that means by 4. So which means the speed of light decreases by 4 times when it enters inside the gallium arsenide from the medium air. So if the speed of light here is 3 into 10 raised to 8 meters per second, here it will be 3 into 10 raised to 8 meter per second divided by 4, which is equal to 0.75 into 10 raised to 8 meter per second. That is what is the meaning. So the wavelength decreases by a factor of 4, speed decreases by a factor of 4. This is what it means. The velocity of light in water is 3/4 of the velocity of light in air. So speed in air, I'm going to consider c, then speed in water c by 3c by 4. Then the velocity is 2/3 in air. So speed in glass, that is equal to 2/3 of the speed of light in air. Now calculate the absolute refractive index of water and absolute refractive index of glass, which means this is medium 2, this is medium 2, medium 1 is air. So always the speed of light in medium 1, that is air, divided by speed of light in water, that is 3 by 4 of the c. This gives me the answer as 4 by 3 is the refractive index of the water. In terms of glass, speed in medium 1 divided by 2 by 3c, again getting cancelled, the answer is 3 by 2c. Correct. Now they are asking us, find the absolute refractive index of water with respect to glass and glass with respect to water. Here you are supposed to use the principle of reversibility of light, correct? Which means that refractive index of medium 2 with respect to 1 is equal to 1 upon refractive index of 1 with respect to 2. So I'm going to find out any one and then I'm going to do the reciprocal, right? So this was the answer to my first problem. Now the second one, I'm going to solve this one, right? That is equal to absolute refractive index of medium 2 upon absolute refractive index of medium 1 with respect to air, whereas this is relative refractive index and these two are absolute. So just now we found out 3 by 2 and this is 4 by 3. So this will be 3 by 2 divided by 4 by 3 or into 3 by 4. So the relative refractive index of glass with respect to water is equal to 9 by 8. So which means the relative refractive index of water with respect to glass will be 1 upon of the glass with respect to water. So this will be my answer as 8 by 9. So finally, this is the answer of the second part. Refractive index of medium is 1.8. Find the velocity, which means I'm going to consider the first medium as air. The ray of light is coming from air and it is hitting the surface and then it is going inside the other medium. Let me call this medium as medium X. And all medium are definitely denser than the air, so it will definitely bend towards the normal. Air is the rarest medium, air or vacuum you can consider in these problems, right? So it is definitely bending towards normal. Here the speed of light is c, here the speed of light is c divided by 1.8. So I must be saying that the speed in x is 1.8 times less than the speed in the air. So I would say 3 into 10 raised to 8 meter per second divided by 1.8, and this answer is somewhere around 1.67 into 10 raised to 8 meter per second. Next question. Here we are given that in medium 1 this is the speed, in medium 2 this is the speed. Refractive index of 2 with respect to 1 is always speed in medium 1 upon speed in medium 2. So plugging in the values, that is 1.8 into 10 raised to 8 meter per second, 2.4 into 10 raised to 8 meter per second, getting cancelled. This is simply 18 by 24, 3 6 18, 3 8 are 24, 2 3s are 6, 2 4s are 8. Answer is 3 by 4. That is the answer. Okay, which is of course 0.75 if you want to still reduce it further because the answer is given. Right. Now calculate the refractive index of medium 2 with respect to medium 1 and medium 1 with respect to medium 2. So this can be very easily solved as applying the principle of reversibility of light. This will be 1 upon 3 by 4. So that is 4 by 3 and this is 4 by 3 is equal to 1.33 roughly. Speed of light in medium A. So medium A, so I would be saying medium A, speed V, velocity in A, 0.72 times C. That means the speed is reducing, right? Because if you multiply any number by less than 1, that number falls down even less than 1. And speed of light in medium 2, that is equal to 0.64 C. Now see, what can be seen from here? If you look at the velocities, then velocity is even lesser in medium B, which means B is even more denser medium, because in the denser medium, the speed of light is even less. Correct? So now velocity of both the mediums are given. Now we are supposed to find out refractive index of medium B with respect to A, and then its opposite. That means this is medium 1, this is medium 2, which means speed of light in medium 1 at the top, B at the bottom. So that means it is 0.72 C upon 0.64 C. Basically, I have calculated this second part first. This part is here. Second medium means where you have the refracted ray, right? And then if you solve this, you will get your answer as 1.125. Correct? Now, simply applying the principle of reversibility of A with respect to B is the reciprocal like this. So 1 upon 1.125, this answer will be 0.89. So moving ahead, here we are given that the velocity of the light is 70% of that of the vacuum. So the speed in vacuum is C. Now the speed in the medium, let's call the medium as medium X, and its speed is Vx. That is 70% of the speed of light in vacuum, or this can be written as 70 upon 100 or 0.7 times C. Correct. Now the refractive index of the medium X is equal to the speed of light in vacuum or the air divided by the speed of light in the medium. So getting cancelled. So this is 10 upon 7. So the answer is 1.43. The ray of light goes from air into a medium. Again, I'm going to call the medium as X and the velocity over there as Vx. The velocity decreases by 20%. That means it remains 80% of the speed of light in air. So the speed of light in air, I'm going to assume C. So speed again in air C, whereas speed in the medium is equal to Vx, that is drops by 20%, so it remains 80% of C, that is 0.8 of C, and the refractive index of medium X is equal to speed in air, that is C or the vacuum, divided by the speed in medium, that is Vx, so C on 0.8 C, and this 1 by 0.8 is 10 upon 8. This can be written as 1.25. That is the answer to the problem. Now, we are given the frequency of the light. So I should be writing 6 into 10 raised to 14. Hertz can be written as 1 upon second also. Now, it goes from air into the water. Calculate the wavelength in water, right? Now, I'm going to use the wave equation. The wave equation states that speed in medium is equal to frequency of light multiplied by the wavelength in the medium. Okay, so the speed of light in the medium, that is the water, that is 2.25, 10 raised to 8 meters per second. Frequency of the light is independent of the medium, so it remains same in all the mediums or the vacuum. 6 into 10 raised to 14 on second times the wavelength in the medium, that is water. So I just want to make a point over here. This is the wavelength in water. So here you must put the speed of light in water. Do not use the speed of light in air over there, right? Getting cancelled. So wavelength in the medium or the water is equal to 2.25, 10 raised to 8 meters upon 6 into 10 raised to 14, right? and then this is equal to wavelength in the medium, 2.25 upon 6. This goes over, so this is 10 raised to minus 6 meters. Now, we do know that 1 angstrom is equal to 10 to the power minus 10 meters. Okay, so then these many meters is equal to, that means 2.25 into 10 raised to minus 6 upon 6 is equal to how many angstroms? So simply you need to divide this number by 10 raised to minus 10 meters, correct? So if you divide this number by 10 raised to minus 10 meters, you will get your answer in angstrom. So this will be 2.25 upon 6 into 10 raised to plus 4, and then the answer will be angstrom, and I leave this calculation on you. You would be getting 3750 angstroms. That is the answer to the problem. Next question, a ray of red light and the violet light travel from air to glass. So already shown that this is a red light, this is a violet light, and both of them, they fall at the same angle. The angle of incidence is same, and this is a piece of glass, correct? Now we do know that the light is composed of 7 colors, white light. All 7 colors, V, I, B, G, Y, O, R, all 7 colors, they travel with same speed in air, 3 into 10 raised to 8 meter per second. So here also, and here also. But when all these 7 colors, when they are made to pass through any other medium, red is always the fastest and violet is always the slowest. These are experimentally observed facts. So instead of going straight like this, the deviation of the red light is going to be the least. So like this is the red light, then again bending out, bending away from the normal, whereas the violet light will bend more and then it will come out like this. And I want to explain why. Consider a river in which the water is flowing in this direction, and a swimmer wants to exactly go on the opposite side of the river. This is where he wants to go. But we do know the fact that the river is going to pull this person somewhere over here. Correct. If the person is very slow in swimming, the river is going to take the person very far away. So this is the expected path where he wants to go, but he would reach somewhere over here if its speed in the water is slow. So lesser the speed, more is the angle of deviation. Wants to go straight, but going in this direction, angle of deviation. So the angle of deviation is inversely proportional to the speed. So red goes with large speed, so less angle of deviation. And where is the angle of deviation? I will show you. This is the angle of deviation, this one. The angle between the extended incident ray and the refracted ray is the angle of deviation. Correct. Now, if I am asked to find even the refractive index, I'll just explain J over here also. So refractive index with the help of red light is equal to speed in the first medium, that is same C, divided by speed of light in the second medium. Here, if I am calculating speed of the refractive index with the help of violet light, speed in medium 1 upon the speed in medium 2. Now, red light travels faster, so this refractive index would be less, whereas violet light travels slower, that this refractive index would be more. So if you measure the refractive index of the violet light, of the glass with respect to violet light, it will be larger than that measured with the help of red light. You can even see that the lateral shift value for the red light is less and the lateral shift value for the violet light is more. Going ahead, just now I explained this part in the eye. So we have two wavelengths, violet light, red light. This is 4000 angstrom, 8000 angstrom. Correct. Velocity is in vacuum, so no matter which color you take, the speed of light in vacuum is always c. So if you find out the velocity of violet light to the velocity of red light, speed in vacuum, it is C upon C. Answer is 1:1 always. Now, the frequencies. So what am I going to do is, speed is equal to this. For red, I am writing wavelength of the red multiplied by the frequency of the red light. For the violet light, the speed is same, C, that is equal to wavelength times the frequency. I am going to take the ratio of these two. So C upon C, that is equal to lambda R times FR, lambda V times FV. So simply I am going to get lambda V upon lambda R, that is equal to frequency of red light upon frequency of violet light. So this is 4000 angstrom divided by 8000 angstrom. So the answer is going to be 1/2, or the frequency of red to the frequency of violet, that is equal to 1:2. That is the answer to the problem. And the first one is 1:1. The wavelength of the light in the medium is 4000 angstrom, not in the air. Whereas the refractive index of the medium is 1.5, and that is absolute, right? Determine the wavelength and frequency in the air. So first of all, we do know that speed of light is equal to, in air, suppose this is the speed, the wave equation in the air, times the frequency. Now if you are using a single colored light, right, frequency remains the same. Any single colored light in air or in vacuum or in water or in glass, frequency remains the same, wavelength and speed differs. So in the medium, its speed becomes V, the wavelength becomes lambda m, frequency remains as it is. Simply by taking the ratio of these two equations, equation 1 divided by equation 2, C by V, lambda A into F upon lambda A into lambda m into F, frequency doesn't change, so cancelled. This is refractive index, that is lambda A upon lambda m, so which is equal to 1.5. Wavelength in the air we don't know, upon 4000 angstrom. So the wavelength in the air is simply these two multiplies, is the answer. The frequency in the air remains the same, that is whatsoever the frequency was, and let's calculate now. C is equal to F into lambda. You can use equation 1 or 2, that's your choice. You will get the same answer because the frequency is independent of the medium. But you need to only be careful that here the wavelength in the air, then the speed in air has to be substituted. Wavelength in air is 6000 into 10 raised to minus 10 meters, because we need to convert that into meters, because over there we have the speed in meters per second. So 3 into 10 raised to 8 meters upon second, 6 into 10 raised to minus 7, right, upon meters. So the frequency, meter getting cancelled, so 3 ones are 3 twos are, so 0.5 into 10 raised to 15, 1 upon second is hertz. So frequency can be written as 5 into 10 raised to 14 hertz. That's the answer to the problem. So guys, I hope that this numerical session was helpful. Do comment in the comment section for any kind of doubts. Do subscribe to the channel, watch all the videos in the playlist. If you have any doubts, again I am saying, please comment in the comment section, do write all the numericals, and have a great day ahead. Thank you for watching.